Chapter 1, and these are the topics: metric prefixes, conversion factors, problem solving, and density. And here are the metric prefixes that you can find on page 21. And we have, going across the top, tera, which means a billion. I'm sorry, not a billion, but a trillion. Right, 10 to the 12th. That's a trillion with a T. You can all those zeros. Giga means a billion. That's 10 to the 9th. Mega means a million, 10 to the 6th. And kilo means 1,000, that's 10 to the 3rd. So you notice over here the equality. Let's start at the bottom. If you have 1,000 meters, that's going to be a kilometer. If you have 1,000,000 grams, you can replace that 10 to the 6th with the capital M for mega. If you have 1,000,000,000 meters, you can replace the 10 to the 9th with giga. This is kind of how the metric system works. All right, we do the same for the tera. Then we have prefixes down here that means less than 1. So deci means a tenth, which we'd write in scientific notation like that. Centi means 100th, 0.01, or this. So you notice, look at the substitution. If you had 1 times 10 to the negative second meters, you can replace this with centi. And then you have milli is 1,000th, 10 to the negative third. Micro, this is really a Greek letter for micro. In this country, though, they use MC for micro. Micro means a millionth of something. Like here is 1 microgram is a millionth of a gram. And then nano means 1 billionth. Notice a 10 to the negative 9th versus 10 to the 9th up here. So 1 nanogram is a billionth of a gram. And then we have pico down here, 1 trillionth. So 1 trillionth of a second is a picosecond. Or 1 second is a trillion picoseconds. So there's always 2 different ways to look at something, and that's what they're really giving you here. Let me pick out, for instance, what that I didn't write on already. How about this one here? If we focus on this one for a sec, what you're saying is 1 microgram is a millionth of a gram, and that's true. Or you could say there are 1,000,000 grams and a million micrograms in a gram. That's true. Most people prefer to look at it this way, the second way than the first. Measuring length, we use a meter as our basic our unit for measuring. It's 1 meter. 1 meter then is 10 decimeters. That's the length of a decimeter. 1 meter is also 100 centimeters. And 1 meter is also 1,000 millimeters. So just like a meter is equal to all of these 3, all these 4 are equal to each other. So 10 decimeters equals 100 centimeters, or 100 centimeters equals 1,000 millimeters. The volume, volume is one of those units that many times you have to derive or calculate. That you can't measure that easily. And if you look down here on the side, that's exactly what they're doing. To find the volume of this cube, they're multiplying the length by the width by the height. So it's 10 times 10 times 10, and they get 1,000. And you multiply the centimeters also by each other, so you get cubic centimeters. And so 1,000 cubic centimeters are the same as 1,000 milliliters, and that's equal to 1 liter. So you notice this up here. 1 cubic centimeter equals a meter. And here we have like a syringe. So 1 cubic centimeter, 1 millimeter, also can be written as cc. Here the cc is short for cubic centimeter. Here we have a fellow working in a hospital who's measuring, or putting up, it looks like one of these IV bags contains 1,000 mLs. Some of you might be doing that soon. Let's take a look at mass now. 1 kilogram, 1,000 grams. 1 gram, 1,000 milligrams. We can write it the opposite way. 1,000th of a gram equals a milligram. Or there are 1,000 micrograms in a milligram. I know it can get kind of confusing sometimes, but after you use these, you'll get used to them. Now let's see how much you know. So you want to stop here and pick out the answers to the 3 questions. So a mass that is 1,000 times greater than a gram would be what? A length that is 1/100th of a meter is, and 3, a unit of time that is 1,000th of a second. And the answers would be, so check your answers now, kilogram, centigram, and millisecond. How about this one here? 4 questions. What would you measure your height in? your mass, the distance between two cities, the width of an artery. Again, write your answers on a piece of paper. So you want to pause the video, and then I'll go over the answers. Okay, here are the answers. Your height in meters. Millimeter would be way, way too small, and a kilometer is way, way too big. Your mass, kilograms. Grams, way too small. Milligrams, even smaller than that. To get an idea about how much you weigh in kilograms, just take your weight in pounds and divide it by 2, and it gives you a rough idea. How about the distance between two cities? That would be kilometers. How about the width of an artery? That's millimeters. Artery is so small. So, indicate the unit that completes each of the following equalities. 1,000 meters is equal to what? 1,000th of a gram is what? 1/10 of a second is? 100th of a meter is. So you want to pause and check your answers. Here are the answers for A, B, C, and D. Don't come out at once. So 1,000 meters is a kilometer. 1,000th of a gram is a milligram. 1/10 of a second is a decisecond. We don't hear that much. And 100th of a meter is a centimeter. Okay. Now using prefixes, I showed this on an earlier slide, but I just want to mention again. Let's say we have 42,000 grams. I can write that in scientific notation, 4.2 times 10 to the 3rd grams. And then because 10 to the 3rd equals kilo, I can write it as 4.2 kilograms. Now, the reason we have all these prefixes is that people get a little uncomfortable with numbers that are bigger than, let's say, the 100. So once you get to 999, they usually come up with a new unit when you get to 1,000 then. So, for instance, grams was fine until we hit 1,000 grams, and then it became a kilogram. Kilograms are fine until you get 1,000 of them. Then 1,000 kilograms is a megagram. Right, next thing, we're on to conversion factors. Any two items that are equal or connected are called conversion factors. Examples would be 1 foot is 12 inches, 1,000 meters is a kilometer, 3 cans for $1.39. So these items don't have to be equal, but they are equal in the first two. They can just be connected like here. We're going to be writing conversion factors as fractions. So we can write each of these as two different fractions. For instance, if you look at this one, we have 1 foot over 12 inches, or 12 inches over 1 foot. So which way we're going to write it will depend on the particular question that we have. And here are some examples of conversion factors here. You've seen all of these on labels before. 16 ounces equals 453 grams, roughly. Here are 3 of them. Look at this here. 16.9 fluid ounces, 1.05 pints, 500 milliliters. So these 3 equal each other. And then over here with the Mayo, 32 fluid ounces is 1 quart, is 0.95 liters. So if you looked at stuff you have at home, you'd see a whole bunch of different conversion factors. Now here's a list, and you'll see this on page 26. Some of these you might know. I'm sure you know some of these, some U.S. conversions. You might know about the quart and the cups. A lot of people don't know that one. Here are some metric ones. Now you should really know a lot of these. If you do, it makes everything so much easier. And then we have metric and U.S. ones. We can use any of these guys to answer questions, which is what we're getting at. So, problem solving is the next topic, and we're going to be using our conversion factors and also significant figures. So, first step is reading the problem, writing down what's given and what you're asked to find. Next, we look for conversion factors to connect them. Third step is setting up the solution, canceling the units. This is the one thing that will let you know that you set it up right, canceling those units. And lastly, we want to round off our answer according to the rules for significant figures. And maybe doing that all semester. So here's an example. My dog's tail is 9.5 inches long. How many centimeters is this? So my given information is 9.5 inches, and my unknown is centimeters. So I need a conversion factor to connect them. So if you went back to a previous slide, you could look that up. you'd find 2.54 centimeters equal an inch. This is the only thing we need because inches and centimeters are in our question, and that's what we have in our conversion factor. So now the next thing is to set up the solution. Now I'm going to draw a line. I'm going to put some numbers on that. I'm going to start off by putting my given information to the left. I'm going to draw a line to separate my conversion factor. Now remember, I'm going to write this in the form of a fraction. So the question is, which will go on top? I have to write it this way because the unit that I start with must be in the denominator. Then I'm going to cancel out those units. So canceling the units is so important because if you would set this up upside down, you'd have centimeters down here and it wouldn't cancel with inches. Now I'm going to do the math and I get this for an answer. So I have to round off according to significant figures. Now the only thing I'm going to use is the given information for that. So 2 significant figures here means 2 significant figures here. And I get then 24 centimeters, which is my 2 significant figures. Okay, not too hard. Let's try another one. Here's my rattlesnake. A rattlesnake is 2.44 meters long. How many centimeters long is the snake? So we write down the given information in our unknown. So we're given 2.44 meters. I want to know how many centimeters. My conversion factor, 100 centimeters equal a meter. Set up my solution. I start with my 2.44 meters. In the textbook, they will write it this way with the multiplying sign and the line for the fraction. I still prefer the other method I showed you. Okay, now what unit has to go down here? It's going to have to be set the meters because I'm starting with meters. So know that this unit has to go right down here. See how it's set up like that? Okay, centimeters on top, cancel the units, do the math, here we go. 3 sig figs and 3 sig figs, so we're all set there. Okay, let's try another one. Now here we have one that we all could do. How many minutes are in 1.4 days? My unknown then is minutes, my given is days. I'm going to have to go this direction though. Days to hours and then hours to minutes. So I'm going to set up 2 conversion factors in a row. So I'm going to use 24 hours in a day and 60 minutes in an hour. So when I go to set that up, I'm going to put both of them in there, so I'm already planning for that. I'm going to put my given information here to start off with. That means I need to have days down here, right? Days has to go there. And I want minutes for an answer. So here's my days. I can cancel that out. And then notice I have hours here now. Hours has to go in the denominator. So I can cancel that out. And I'm all set. I have minutes for an answer. I have minutes here. And I multiply across the top. And round off for 2 significant figures, because this is 2 up here. 2 significant figures. And I get 2016. Well, that's 4 significant figures. So here is where I want to write this number in scientific notation. So if I write it like this, here's my 2 significant figures, and I'm all set. So this is the best answer. Now this is a good answer, the first one, but it's not the best. So full credit for the final answer. This is partial credit. Next topic is density. Here we're going to be comparing the mass to its volume. It's also the mass of the substance divided by its volume. And here is the formula for density. Density is mass divided by the volume. The units would be grams per milliliter or grams per cubic centimeter, which usually we write like that. So density is one of these physical properties of matter. It's something that we have to calculate. And this we had earlier, but it's something good to note. 1 ml equals 1 cubic centimeter. And if you go to page 33, you would see some of these densities listed. So, this is at 25 centigrade, which indicates that temperature is important. Cork, very small density. Look at some of these. Lead, gold, silver, very high. Metals have higher densities. Aluminum's kind of small. Cement. You might think cement is way up here, yet, if you took a small bit of cement that would occupy a milliliter, it would weigh more than 3 grams. Liquids, gasoline. You notice that less than 1, water is 1. The units at 1 gram per milliliter. Except for mercury, the densities of all the liquids are pretty low. Metals are pretty high. Now we have gases. Now you notice that here they had it measured in grams per liter because gases weigh so little. All the others were grams per milliliter. And even though you measured it for a whole liter of it, it still is pretty small. Okay. Now let's do a problem finding density. So osmium is a very dense metal. What is its density? They want the density, and they give you 50 grams of osmium and the volume of 22 cubic centimeters. So we have our formula. All you have to do is make our substitutions, and then we do the math and round off with 3 significant figures, since that's what we have here. And this is our final. So that's our 3 sig figures. Pretty straightforward. Now here's one where we're going to find, first of all, the volume of an object that's hard to measure, and we're going to use what we call displacement of water. So what we do is we take a graduated cylinder and we put a liquid into it whose volume we can read. So this is 35.5 milliliters, so we got that. And then we take our object and we drop the object in. Now when that happens, the volume then goes up. And the volume will go up by the volume of the object. So all we have to do then is subtract the volumes and we get 9.5 mLs. So 9.5 mLs is the volume of the piece of metal. And this is zinc metal. Notice it says zinc down here. Right. Now, if we wanted to find the density of that piece of zinc, we'd have to get its mass. So weight on the scale. And then we would take that mass and divide it by the volume from the previous slide. You notice 4 significant figures on the top, only 2 on the bottom, would give us 7.2 grams per cm cubed, cubic centimeters, as the density for the zinc. Now we can use densities to determine if something would sink or float in a liquid. So here we have a beaker that has water in it. It's all water. And you notice some objects are floating, some are sinking. So the lead and the aluminum both sank in the water, and the ice floated on right about at the surface, in the cork above the surface. And so we can do that because things that have a density less than water will float in water for the most part, and those that have densities greater than water would sink. Now here's one for you to try. Which diagram correctly represents the liquid layers in the cylinder? So we have Karo syrup, that's on the K, that's 1.4 grams per milliliter, oil 0.91, and water 1.0. So take a second to look at the diagram. You might want to pause this, and then come back and we'll check out the answer. So which one has the greatest density? That's the syrup, so the syrup has to be on the bottom. Well, there's only one with the syrup on the bottom, so that's this guy here, so that's our answer. So you notice 1.4, the water is 1, and 0.91. Okay. Now, density can be used as a conversion factor. Here's a density here, 3.8 grams per milliliter. The equality would be this. And once we have it like this, we can write it as a fraction. We can write it either 3.8 over 1 ml or 1 m over 3.8. So we don't really need a formula if we want to use density in a calculation. And here's an example. Let's say we want to find the mass in kilograms of 875 milliliters of octane, and here's the density of the octane. So we're given 875 mLs, how many kilograms? And you notice that the density is in grams per milliliter. So I'm given grams, but I have to get kilograms. Okay. So I'm going to take my 875 mLs. I'm going to multiply it by the density. See, milliliters will cancel. I would have grams for an answer. And then I'm going to multiply that by 1 kilogram over 1,000 grams. And I get my answer. 3 significant figures because of 3 significant figures. All right, you try this one now, and then come back and see the solution. So I'm going to pause the video. If olive oil has a density of 0.92 grams per ml, how many liters of olive oil are in 275 grams of olive oil? So we're given 285 grams, and we want liters. So we're going to have to take out 285 grams, and then we're going to have to use the density, because that's grams per milliliter, and we can figure out how many milliliters that will be. So you notice I had to invert my density. I can cancel out my grams this way. So if I did the math, I get milliliters for an answer. And then lastly is to convert milliliters to liters. And I get 0.31. 0 liters. Now why 0? Because 3 significant figures go along with the 3 significant figures here in the given. The 0.92, we didn't measure that in the problem. That would have been a definition, that density. That's why we're not considering that for rounding. And that's the end of the show.